Anyone remember that we did that?
Yeah.
Yes, right? We glued this band thing and we cut it and it was like one piece, right? So why did we do that? Okay. So basically, when you, that's my Möbius band, right? 然后 we glue this together like this, right? Okay, if you cut it like this, right? We are gluing this part to this part and this part to this part, right? That's why everything is one piece only, okay? The other interpretation is for every point here, I attach 2 points. One in the upper part and one in the lower part, right? So, or if you prefer, I go in the third dimension. For every point of my band, I have 1 point here, and I'm 1 point I go back a little bit. So every point has 2 points. And the question is now, the new object I have, by assigning to every point on my band 2 points, okay? The question is it connected or disconnected? Right? For if I would have a normal strip, I would assign to every point a point on this side and a point on the other side. What I get are 2 strips, right? One in the front, one in the back. When I have a Möbius band, if I do that, I will have one in the front and one in the back, but then they are somehow tucked to each other. So I only have 1 band, right? So depending on this thing, this is non-orientable. That's the math word. And this is orientable. So cutting this thing open by assigning a point on the one side of the band and assigning a point on the other side of the band, that thing is called orientation cover. So it's a 2, 2, 1 cover because at every point I have 1 and 2 points. Okay? And the question is, my final object, so when I cut this thing open, is it 1 thing or 2 things? Okay? 1 thing means my original one is not oriented. Okay? Because it doesn't have a side. Yeah? No inside and outside. If I have 2 pieces, that means I have an inside and outside. Namely, the one band I have is inside and the other band I have is outside, or other way around. Right? While when I do it here, I do inside, I do outside at every point, but then it got stuck together. Obviously not. Yeah? So, but when I do that twice, so the second time with the Möbius band, inside and outside, right? What happens is that I get I get 2 sides because I defined now what inside and outside is. Right? Because basically, I have a plus sign and a minus sign that gets tucked together, right? And now when I do it twice at each of these signs, it stays plus. Like minus is also plus. So that's the reason. Okay? So today, we will see at the very end, hopefully, something about the Möbius band. Okay? That's why I'm repeating this again. The other thing we did are Platonic solids. Also, this I would like to tell you what happened, right? We classified using the equation that the number of sides at each vertex, right, times the angle of the regular n-gon is smaller 2 pi, and then we just computed m and n. N is n-gon, lar n-gon, and m is the number of sides per vertex. Yes? Okay, so there's only finitely many combinations, 5, where this works. And the crucial thing is this inequality, which guarantees that this thing is so-called convex, right? Okay. So I would like to say, if you have something discrete, which has finite faces everywhere, this thing is called positive curvature. Why? Because it looks like a sphere. So, curvature. Now, one question for you: what would be negative curvature? Yes, but how to do that with this equation? But how do you... Yes.
A negative curvature.
Yes. For example, what is the characteristic of negative curvature, though?
内角和就是三角形内角和小于2派。我是这么
Oh, no holonomy. Just, you're right. Just the simplest answer is just bigger than 2 pi, right? And equal to pi would be plane, right? If I put all the faces together and this makes me 2 pi, that means everything is flat, right? So bigger is when I have too many faces, basically, for one thing. So it would curve around my point, like, just goes around. If you have too much of paper and then try to do the cone, so that's a positive curvature, right? Everything is smooth. Well, not smooth, even out. But if you have too much of it, if you just put a lot of papers together and you want to make a cone, what happens? It gets wavy outside. So that's how negative curvature would look like, in a sense, right? Of course, basically the idea is at every point, the curves here bend in different directions, one in this side and one in other side, while on the sphere, the thing bent in the same side, okay? But of course, this is a smooth notion, while this one is a discrete notion, okay? Because this is not, the edges are discrete. It's not bent, yeah? Okay, it's always continuous. Okay, good. That's something we will come to later, okay? So that's the last thing we did was this plane thing, okay? So we had these axioms and we said, okay, let's see. Let me just do this. Okay. The last thing we had was the plane, right? We had the axioms, yeah? How my plane corresponds to R2 and vice versa. Okay? That we did, right? How to do that was we chose A, B, C, 3 different points that does not lie on the line. And we said I give A my coordinate 0, 0, B my coordinate 1, 0, and C my coordinate 0, 1. Any other point, if I just draw the picture, get the coordinate, and I should not, maybe I shouldn't, for example, D, the coordinate by taking, that's my line defined by AB, that's uniquely defined. I take the parallel to that line, and I should just draw it here. It intersects the other line at this point. And this point I call Y, 0, 0Y, basically, right? And I do this the same, and I should not draw the thing where take the parallel here, take the intersection point, this thing I call x0, and then the coordinates of D would be x, y. Yes, that's how I define my map from P to R2 or R2 to P, if you like. Okay? Okay. And now the idea is when are segments the same? Segments are the same if they are congruent to the same x0. So basically, main x would be the length of my segment, right? And if it's congruent to x0, then meaning they have the same length, yeah? Because we haven't defined length yet. Right? Okay. Now what about angles? When are angles the same? So you have this idea of what is a 90-degree angle, what is a 30-degree angle, right? But in our definition, how do you attach a number to an angle? Sorry, I think maybe just now close the windows. 有点冷是吧？哦，高一点吧，我说啊 ，it's okay, it's okay, it's close now. Oh. But 可是我们直角已经有个定义了，是不是？我们说这个直角的定义在这个 P 上面的定义是，如果这个是 A B C， 画的斜一点啊 ，C， 那么 A B C 和 A minus B D C 的这个两个是一样的，才是直角。所以我们在 P 里面已经有个直角的概念了。
我们有直角。
Right? So now, what about the angles in R2? So how to attach a number? OK， 如果我们说这个是90度，那360度是什么？180度是什么？那我们可以做45度吗？如果我们说这个是90度，那么一半是什么？
一半应该是就取的那个。
They are filming, but they are not streaming. 这for me, come on.
X 等于 Y 的时候。
你。
画呀，画出来呀。
这个就是 X 然后 Y 然后一个连线然后 X Y 的。
这个是在 R2 上面可以这么做，那 P 里面是怎么办呢？
需要平面。
平面。
就是说你随便什么个角，怎么样子分成一半。Wait a sec. Let others think as well. Yes.
Straight edge and compass.
是规作图被允许吗？
可以。
I know.
尺规作图就是先定一个直角， 然后这么往前怎么设计？
Yeah, just wait a sec. Let the others think as well. 让他们先给他们一点时间。
应该是在这边找一个点，使它到这两个点的距离相等。然后这个连线就应该45。
哦，那怎么找这个怎么找这个点呢？
我来吧。
等一下。
老师那就做
给他一点。
圆的。
对啊，怎么做呢？
做呀，对呀，做呀。
怎么做吗？
人呢？我做呀，你做呀。
You have it almost， 差不多就是这个样子，对。
就是做两个然后就是先取这两个相等嘛，然后这个焦点，它这个焦点画在有4度。
Perfect， 对。Okay? Have you understood? Shall I repeat? Yes, repeat. Yes, let me repeat. How to do it. So, if I have an angle, doesn't need to be right, it could be any. Okay. The idea is I have the origin, the intersection point, and another point, right? That would define me a line. And it would be half of each, these two things would be the same if the distance between this point and this line is the same as this point with this line, right? So how to do that? Well, if I have a compass, I can do it by going one in this direction, the same one in the other direction, right? And then I just just put my compass here, put some R in this direction, and R in that other direction. Put it here with the R, like this. Then this point has distance R to this point, and distance R to that point, which has the same distance as here. So if I now connect, it will have the same distance to both lines. Okay? So I didn't need anything. I don't need to compute. I don't need to whatever measure. I just need a compass and what is 1. The same distances would be known. Okay? So that's how I have angles, and then I can do a third and so on and so forth. Okay? Good.
I think you can say how much the angle is to all r and mod 2 pi z.
Yes. So now it's possible to say what 4 times a certain angle is, because I just start out with 1, right, with 1 angle, and then I start with this one, this line, and then just copy this angle here. That's with twice the angle, 3 times the angle, and so on. So we can do computations by adding and subtracting angles, right? Okay. Now, this seems to be rather, so the way to do it, so that the angle we want, we see on my blackboard, and the angles we would have on P is the same, is by choosing this line and this line being perpendicular, right? And that is the notion we have in P. It's not necessary, because we can choose something else. But let me give you something that would do length and angles at once. What could that be? Something that measures angles and length at once. I just write this down, and then it tell me why this is the case, okay? I have a map, which is this bracket. Probably have seen that.
Okay.
This point means I can put something in. Yes, I just write it this way. So I have 2 vectors, 2 points, with coordinates. Let me call it this way. So this gives me a point in my plane. This gives me another point in my plane. Okay? And that maps to R by giving this thing, mapping it to x1, x2 plus y1, y2. We just multiply the x coordinates and the y coordinates. Okay? So now, when I have that, why does it measure my length and angle simultaneously? Wait. Why does it measure angle and length simultaneously? Why does it measure length? Maybe it's easier. Why does it measure length? So if you have a point x0 and another point x0, what would you get? X0 is my point here, this point. Okay, I plug it in here. What do I get?
0. X squared.
Yes. Okay, that's x squared. So, what is the length of that vector?
X.
Yeah? Is the length the vector?
The square root of a vector.
So that means x, well, it could be negative, right? But it's just a square root of this thing with itself. Yeah? Okay. Now, if I put, I do this.
X squared plus y squared. And
What is this?
S oh and
It gives
and
norm on
V
that too.
and
Which
V,
which point is it? What is this point? X, y.
point X Y.
What is it? Where is it? Can you draw for me?
Okay.
And where is it? X? What is X here? Okay. Yeah.
Yes.
Okay. Don't. Okay. Perfect. So, what we have here is this one has length y, right? This one has length x. And I'm looking at the length of this vector, which should be the square root of this here, right? It's the length of this vector. Okay? What we have here is Pythagoras, right? That's the theorem we had. Yes, last time. Saying in a right angled triangle, x squared plus y squared is length of this one squared. Okay? So if I have a scalar product, that's what this thing is called,
Scalar product.
then the Pythagoras is already built in. Yeah? So we start with Pythagoras basically as part of the axioms rather than as part of as a theorem. Yeah? Okay? So the question is now, if I have the norm, okay, that's what it's called. If you put in here and here the same thing, that is called norm. So instead of writing it twice, that's unnerving, right? You have to write the same thing twice. We are kind of very lazy. We write this. Just to say that's the same thing we're putting twice. Yeah? It's kind of a square.
The norm is always non-negative.
Yes, because we only have squares on the right-hand side. What else do we have?
and we have the angle. For example, you can choose 0 and 1, 0. And this makes a circle. And for all the points in that circle, norm of 8 and 1, 0 is just cosine of the angle.
That would define the cosine of the angle, but the question is, why would that even make? I mean, from this perspective, why is it that this would define the angle? Okay, so let me just emphasize certain things here. When you have the norm, meaning the value, the length of any vector, then you also have the scalar product. Why? Because you can just compute. It's the scalar product is called product because it's like multiplication. You really multiply the left side with the right side. Okay? So if you just have this, now it's too warm. If I open the window, it's too cold, right? Let me, no, that was not what I wanted. y1 plus x2, y2, x1, y1 plus x2, y2. You can multiply this out. It's the same as x1, y1. I'm just doing this for you, just for this time, because this is kind of, you have to write a lot. Plus, yes, that's, yeah. Have it twice because we have one, like this. Plus x1, y1 with itself. Plus x2, y2 with itself. I mean, it just compute from here with this formula that on left and right hand side, it's the same. Okay? What you see is this here is a norm. It's a norm of x1, y1 plus x2, y2 squared, right? The right-hand side is norm of x1, y1 squared plus, and again we have Pythagoras. Yeah? And this is a scalar product. So the scalar product is defined using 3 norms uniquely. That's one thing. And second, it's perpendicular if and only if I have Pythagoras. Okay? So in this way, we have both length but also the angle, because this term makes me how the length here is not quite the sum squared, right? Depending on what value we have here. Okay? Good. So if you have all the axioms we have, then the most important quantities are length and angle. Now going to something else. Yeah, I said today we want to do projective geometry. Okay? What is projective geometry? 叫啥呀？摄影几何。Okay. Do you know why projective geometry exists? Have you an idea of why projective geometry exists? Why were people interested in that? Why is the name projective geometry?
Is it because there's more than 3D?
Roughly. I mean, it's 3D, and we want to do it with 2D. So we have actually more dimension than we can capture. Okay? That's basically the idea. So let me draw a picture. And I will tell you what it has, why we want to compare this one with something else we can do on the plane. Okay? So this is my eye. So that's us. Okay? That's my eye, and that's my, you can say that is my 0 point in, that's my origin in my brain. Then I have some object here, and since I cannot draw very well on the blackboard, let me draw a cube. Okay? Well, you see already, when I draw a cube, we know in reality, this angle is actually a right angle, right? But why do I draw it in a way that is not a right angle on my blackboard?
Something is lost. Something is.
But it kind of has an appearance of a right angle, although I'm not drawing it that way, right? So what we see on the board resembles and somehow fake it for our brain that this should be a right angle picture. Okay? Because we are reducing something 3D to the plane. Okay? So this was invented because people wanted to draw. So it actually was invented by Italian painters.
Want to draw a 3D picture?
Yes. When we want to draw a 3D picture realistically on a canvas or paper or whatever, right? So the Italians in the 1500s, if you go to a museum and look at these pictures that are older, you will see they look really awkward, okay? Because they didn't know what that is, okay? So you have the 3D object, and then I have some plane. Let's see. That's my paper, my canvas, whatever. And this is not how this should look like. Okay, like this, okay? That's my paper. So now, how does this cube look on paper? Any idea? What is the optimal way to draw this cube on this paper if I'm sitting here and watching this thing? How would you draw the optimal point? Oh, wait, let them think a little bit. It doesn't matter. Just any paper, yeah, away from me. So that's what you want to say as well? What did you want to say? How to do it?
We need to draw the cube on the canvas. Okay, just connect a point to.
That's what. Yeah, that's what. What? Not.
On the cube,
What? Sitong. That's right. What you said as well. Okay. So, correct, right? You draw whatever point you wanted to out of a cube. You connect it where we are, and then the extension where it hits the plane, that's my picture point. Okay? Meaning, every point on this line will be mapped onto that point. Okay? On paper, canvas, paper. That means paper. Okay? So, what this geometry is about to say is, instead of lines in R3, I look at points representing my lines. Yeah? Well, they are really points because they are points on this paper. Okay? So that's the first philosophy of projective geometry. Right? Points are
as lines.
yes. So lines are now points.
We can exchange them.
Yeah.
Whenever we want.
Okay. That's the first thing. What else should be in projective geometry? Well, that's a philosophy. Now, let us work a little bit harder to see what we get from here. Okay, when we have this philosophy that now every line gives me a point. So but it's not quite, well, it's rather like this. Lines in the 3D gives me points in 2D, right? Okay? Yes. Okay, let's look at this again, other picture. Okay, I have my eye here, my 0. This is my canvas. Let me, how to draw it, but like this. My paper. Okay? And then, let's assume I have some ceiling. Okay? Like this. Okay? My eye might be at 0. Okay? 0, 0, 0. All the coordinates are 0 in 3D. Yeah? Now, my canvas, I just pretend it to be at y equals 1. Meaning, this is the set of points where I have x, 1, z, where x can be arbitrary, z can be arbitrary. Yeah? For example, 3, 1, 4 is in this plane here. As long as this in the middle is 1, I have what point here? Okay? So that's why you see this is 2-dimensional because I have a freedom x and a freedom z. Okay. This here, that could be my ceiling of my room, for example, or the sky, if I want to draw it. That could be at z equals 1. That's correct. So these are the points. Let me just draw it this way. X, y, 1. Okay? So now, wait a sec. Let us consider lines on there, parallel lines. 1, 2, 3. First, what are these sets? Parallel lines. What could be those sets? That's my first question. Or lines, how to write it with x, y, and z, okay? And second, how do they look like on paper? Give you 5 minutes, just think about it, okay?热一会儿冷的。What do you think? What do you think? 只是在想，想什么呢？
在想问题。
Okay, what are lines? How would lines look like actually in R3 or in R2? Let me. How do lines look like in R2? Yeah. 直线，如果这个要写这个 equation， 那是怎么写？
写 x 加几 y，ax 加 b y ，ax 加 b y 加 c
等于什么？
ax 加 b 等于。
那 y 呢？
等于 y 等于 y。
等于 y。啊，那么 如果我要写这个点儿，然后这个应该是 x, y，right？ 那怎么写呢？You can have that way, yes. But then how to write the points here? 那这个点儿是什么呢？
你要出现竖线它就废了。
那这个是什么呢？
It is used. I can use this. It is x. And
那 b 等于0呢？
还有一种挡住的。
b 等于0，它们就是 x 等于 c 那种形式。然后那就是 x 是 c， 就是 c 是一个常数，因为它还有竖线。
对。So actually this is enough， 因为这个两个的东西是一样的。
但是就是下面那个为了表示严谨，就不然它上面那个应该表示竖线。
你有竖。Yeah. So, okay, you can see here how a line is parameterized if you want to write these sets by just writing x or whatever. Well, you can have an a here if you like, but basically something ax plus a, right? Okay, in a sense. Or the other point would be here it being 0. So how do you do that here?
Or you mean all lines is 3 dimensional?
Yes, these purple lines. How to write that? And how to ensure that they are parallel? What does it mean that they are parallel? 就是平行的，就是我想写3个，这个直线需要平行的，一个是这样的，那我叫这个的平行线，那怎么画？怎么写呢？这之类的 ，how are the equations？
那个 a 要有，然后。
Wait a second. Let that.
三维图。
It is ax 加 ax plus b prime maybe.
Yeah. Right. You want? Yeah. Yes.
In R and
No, just R3, please. It's the same thing, yeah.
这是三维的平行。
对。
C1 equals 0, and the set of these parallel to A1x plus A2y plus A4 and plus C2 equals 0. And for C1 and C2 in R.
That is correct, but well, we want what does parallel? Well, let me put it this way: what does parallel mean in R3? 就指平线，在三维是什么？
They'll never have an intersection.
R3里面
就是他们俩的那一个平面
平行的面吗？
不是就是这两条平行线里头共。
平行线在三维里面怎么定义的呢？
Not intersecting and in the plane.
就是他们俩不相交，他们俩在同一平面里。
Right.
在一个平面内且不相交的直线。
Correct. Okay. So because otherwise you can have these lines, they're not intersecting as well. Okay. Good. Now, if we have this, how do they look like here?
That is x1 okay. Oh my god.
Give the others a sec. Give others a sec to think. So if you know how these are looking like, then I ask you, how do they look like on the plane projected? Right? With this idea that you would pass from your origin a point to the thing and then project it on the canvas. Okay? And then try to draw a picture. Okay? You can start with a picture first. How would you draw these lines? How would the picture be of these lines on this canvas? What do you think what it should be?
It's also lines.
Lines.
And lines is all the lines and they're parallel to each other too. Pretty high and maybe there.
Yes, and the second line? And the third line?
Yes.
And they are parallel?
That's there.
What's your opinion on this? You're not sure whether it's parallel? Why are you sure or not sure that they are parallel?
Suppose they are not parallel. Then suppose they are not parallel, then it's a mapping from this to there. It's from there, but there are two points at the outside because they are parallel and
To what?
because there's a mapping from the point from the upper plane to the lower plane.
And what should that map satisfy?
That is from 0, 0, 2 to that, the points in there, and it gives a point in another one using the.
Why is this the case?
Using that.
So every upper point definitely give a point here.
Yeah.
But why should every point here give a point upstairs?
Because you can just rotate it and just like
Maybe you should give me the formula for this line and the formula for this line. What do you think we should look? What do you think how this should look like? Do you want to draw a picture? How this would look like? Do you think it's parallel? Yes. Maybe you should also just compute the formula for the lines.
I think you have the lines in the wrong points.
Maybe you draw a picture as well?
Yeah.
Show me a picture. You never had a drawing class? No. Yes, just if you're late and whatever, take whatever. I don't need to be so tidy. You think they are parallel?
Probably because if they are parallel here, like the spaces are the
Yeah, but downstairs here, are they still parallel? Not
the straight lines. The straight lines.
Yes, but are these straight lines parallel? Are they like this, or are they different? Maybe you should write down the formula, and then you will see. Right? That's actually, take the simplest possible purple line you can have. The simplest possible. Just one example. Yeah. Just the simplest, just one example. Okay? And then see what happens. Don't take A and B, okay? Just take one. 0, 1, or whatever. Eh? A equals 0, B equals 1, and put it there.
Oh.
And it gives me 3 different lines. Order wrong, but what I said before. Oh no, actually it's fine. Oh well. Shall I give you lines? Do you have the lines? Do you know the lines?
I got it.
You got the lines? Can you write the lines first? What are the purple lines? Yes, write down the purple lines first, maybe. Here, you can write it here.
This is one of the lines, maybe.
Yeah, but can you write it in coordinates with x, y, z, like 3 things? Exactly. Now another line. I would like a parallel line. And another line? Good. So these are my 3 lines. Now, how do they look like? Here. On my y equals 1. Okay. I connect my 0. Well. Oh, goodness. take a nicer one. Let me just go through this first. Like this, right? Okay, this here is 1, y, 1. What is the coordinate here? This here is 0, 0, 0. So what is this line? So this is 1 over y, 1 over y, right? Because, yeah, just this is basically this here minus this point, and then I scale. Yeah, so this is, if I had this thing called b, then it's b minus 0, which doesn't change anything, and then I just take a scale of it, t. That's my line. Okay? For every t, I get a point here. And t can be just some real number. Like for 0, I have this point. For 1, I have this point. And for everything in between, I get all the line. Okay? So it hits this point if my second coordinate is 1. So t times 1, y, 1, right, is my line. And the question is what t, for what t is t times, is equals t, y. For what t is t times y 1, and that is 1 over y.
Yeah,
So that's why.
All the points x, y, 1 maps into y over x over y 1.
So now if that's 1 over y 1, 1 over y, what are the other points on this thing? So these are lines, not points, right? So it's like, this is the one line. One line looks like this. What are, for these ones, what are they? So that's maybe L1, L2, L3. And the points on the canvas, I can call L1. It's tilde. I have this as 1. What are those?
And the inverse mapping is x, y, y to x over y, 1 over y.
So it's 2 over y, 1 over y. L3 is 3 over y, 1 over y. Okay, now, if you draw this curve, these lines, do you think they have an intersection point? Are they really parallel? Are they parallel?
Y equals 1. And then you can find the point y such that 1 over y equals 2 over y, or I over y equals g over y, or is not equal to k. But this is that y is not 0.
What?
And that time is intersect at the infinity.
Okay. So when y becomes very, very large, okay, this point here is very close to 0, 1, 0. This point is very close to 0, 1, 0. And this point is also very close to 0, 1, 0, which is, let's say, this point. Okay? So, if, let me just, these are my initial points of the line, which projects to this thing.
Oh, I got it.
Then the projections will go in this direction. And they will not be parallel, because for y goes to infinity, they intersect.
They don't intersect, but they're not.
I mean, the lines here intersect. The purple lines don't intersect. Okay?
Okay.
So this now is called vanishing point. Okay? Because it's kind of an imaginary point, right? Where all the parallel lines in the ceiling here, if you project down, would intersect. So maybe if we want to do a nice picture, we need to add that point. Is this the only point which is imaginary? are there more points that are imaginary? 就是说假的，因为这个在三维里面其实是这个里面这上面没有的，根本就没有这个点，是不是？这个点儿，如果你要真的是回去放到这上面的话，不是在
is 没有焦点。
对，是假的一个焦点。
确实会有焦点，但是它不平行。
消失点。
So are there more points like that? What happens if I take blue, do these parallel lines? How do they look like?
Oh, I must have a vanishing point. Oh, it's another vanishing point.
Actually, if there's a point there, for example, x, y, y. Then if you draw a line from this, and in this point, the image of it is y. Y and it's 1 and 1 over y. And if there's a point x, y, z. No, x1,
One.
x1, y, z. Then there's an image of it. For example, this point, then it is x over y, 1 over y, 1.
Yes. But the question is, do we have more of those imaginary points? Yeah? How many? How do they look like? You have almost have it here.
A line.
A line. What kind of line?
All those vanishing points
In this particular class.
merge into a line.
And what is the equation of the line?
I'll get one. Maybe 0. Oh no. X1 0. Okay.
Yes. Because here y can be very large,
Okay.
right? And then it goes, say x1 0. Because this definitely is a plane where z becomes 0. Okay? So that's called, this thing is called horizon. Horizon. Why is it called horizon?
地平线
Why is it called horizon? Well,
Because when you look at something far away, then you will find, and the horizon is where the land and the sky intersect.
yes. Because if you are, at the sea, right, and you go for the beach, and then you will see there's a line where sky and sea touches. And this thing is the horizon, because these are the points where the infinitely many parallel lines in all different directions would meet. Okay, on the ceiling and on the floor. Okay. So if you want to draw nice pictures, then you better add this line to your picture. That's a first. And second, you better give up that parallel lines don't intersect because they intersect. Okay? So let me just write this down. That's the problem, you have wet chalk. So the reason for projective geometry is really drawing, okay? And every seeing like Riemannians and so on, it's just a generalization. Everything works just the same. Okay, there's no super lot of added complexity to it. Yeah. So, first, add horizon. Well, before that, maybe all lines intersect.
Define a line, vice versa.
Yes, but all lines intersect. So instead of the parallel axiom we have with Hilbert or Euclid, we take the new axiom, which is saying all lines intersect in a point. Okay?
It's a case 3-1 without 0.
Yes. So again, we take coordinates because we want to understand how this looks like. Okay? If I have x, y, z, which is not 0, 0, 0, then obviously this one defines me a line because 2 points always define a line, right? And these 2 points lie on the same line. Same line. Yeah, you can call it lambda. We call it t before. So if I scale this point and I can get to that point, then they lie on the same line, right? So meaning some t. Okay?
By the way, teacher, I have some things to say.
Yeah.
If you let all those lines in the point and the set of it forms RP2.
Yeah. That, well, it's called RP2. That's true.
Yes. Then first that S2 for example, there's a mapping from S and from R3 cross to R3 cross let's M2 and all the points P to over the norm of P. And then then let S2, and then S2 is the image of S.
Yes.
So we know that RV2 is as a comparison to R3 is these
Yes.
R3 cross. And by using this definition, we also know that RV2 is isomorphic to S2 over V2. If you say S2 as a group, and it means that for P, it should say as negative P.
Yes.
And this is a suppose F and G. Suppose F and G are polynomials and with degree m and n. And they have no common have no common divisor. Then the variety a variety of F and G we can consider it in RP2. For example, for some P in
Why do you need that it's homogeneous?
homogeneous 其次的
Yes, why do you need that?
because it's redundant, and then the I, P, V, F, V, G, and this equals M times N. And this is the case when
Well, what does it?
this is the case when M and N equals 1.
Okay. Well, can I just continue what I had here? Because we are arriving here anyway. Okay?
R cross.
Just R without 0. Or without 0. Without 0, 0, 0.
Because 3 is field.
Let me explain this first. And okay, so all the lines are the same because we project, right? Because our observer is at one point, and all the lines are projected on the same point at the paper. So when I have a T, meaning I'm moving along the line, nothing changes. So I identified with the same point. Okay? So now, since I can move T, and my x, y, z is not 0, I can take the length of that vector, right? So I can take the length of that vector times my x, y, z, right? And that would represent me my point. So this one is in the 2 sphere because that has length 1. This here has length 1. And then, okay? So now my new, I just, instead of considering all planes, I can consider only S2s. And I didn't say it's equivalent. I didn't, I'm not there yet. Wait. Yes. Well. We are here, okay? If I'm already, both points are in S2, and I ask when exists a T such that these two are the same, now, it actually doesn't matter because it's both are non-zero, so it must be on non-zero. Then the only solution is either x is plus minus x tilde, or y equals plus minus y tilde, and z equals z tilde plus minus, right? Otherwise, it cannot be both in S2 and, because the set is by x squared plus y squared plus z squared equals 1. And for x tilde as well. Okay? So now, this means I have a little sphere. Ah, damn. Okay. I think that's enough. I have a sphere. That's my S2. And I say this line here, which intersect my sphere twice, right? These 2 points are the same. Okay? Because this point and this point are on the same line, so if I project, it will be the same point. Yes? So now that's true for every line. So all the antipodal points are the same.
然后这个对这条线有什么要求吗？还是
只要是从零过。Okay. So now, what is the space? What does the space look like? What is RP2? This space is called RP2, but what is the space?
For example,
No, I want the picture, not the definition.
okay.
I want the picture, not the definition. First,
picture, I got it. You can draw RP2 as like this. You have I2, and you connect it like this. And each point, for example, this, suppose this, this has the coordinates, something x and 1. Then I say that I should claim that this is the same is 1 minus x 0. And for a point there, we say that y and not 0 y, and this is 1 minus y, and this gives equivalent in partial of I2. This gives a relation, and we consider this I2 this relation, and you can prove that this is isomorphic to RB2.
Yes, but how does it relate to something we had before?
Yes, Klein bottle.
Well, this is a Klein bottle, but we didn't do a Klein bottle here.
Yes.
What did we do?
And you cannot draw it in the three-dimensional space.
Well, we can draw, but
no, there's no such kind of things. Absolutely.
oh well, you can.
We can't
Oh.
do it because yes, you cannot build it because they're
well, it's self-intersection, but it's not. We cannot build it.
yes.
So another picture.
And another, I have another.
No, let
Suppose there's a Mobius strip.
Yes.
There's a Mobius strip, and you know that the boundary of it is a circle, and there's also B2, and this is M. Then for some, it gives it orientation, and for there's a one-to-one as a homeomorphism map. For example, this is a point in the boundary of Mobius strip is a point in B2, and this
Yes.
the mapping, and we shall say and consider the B2 over this relation, and we can know that this RP2 is isomorphic to this.
Yes. Let me just draw a picture in the sphere for this. Okay. You cut out the disk, throw it away.
Yes.
Throw it away. But now, since this part and this part is identified, right? Because this point and this point is supposed to be the same. You also throw this part away.
Yes.
Okay? Now, wait a sec. Let me just do the colors so that you can see it. So now what you have is the middle strip, right? Which is a strip. But what we do is this point and this point is identified. This point and this point is identified. Meaning, if I have this edge, like this, I'm gluing it like this. Okay, so that's why this one in the middle is a Mobius strip, and we have just removed the disk. Okay, we remove the disk. 我们把这个丢掉了. So that's why you can get your Mobius strip from the sphere with the antipodal point put together. So it's the same thing, just in a picture where you can see. Okay? Okay, that's all for today. I was told it's too long and you need pause. And but if you want to discuss, I'm still here. Okay? But thank you very much. We'll continue next week.